condensed granular flows on an inclined plane.
Okay, so this is something that Michel has explained on the first day, and many others have explained during the course of this. If you have a flat frictional base, you have a plug and a shear at the bottom. If you have a bumpy base, it sort of shears homogeneously. And if you have an erodible bed, there's a solid bed on which there's a thin layer flowing. And we were trying to see, I mean, from a continuum rheology point of view, so it's sort of a puzzle that, as the thing is starting to flow, a particle in the middle knows what the base is like. And that's sort of counterintuitive to rheology, where you expect the response to be related to the forcing at that particular location. So we were trying to see in simulations how this transition happens. This is a purely simulation study, so I'll try to tell you what exactly we did and what results we got, and try to make some sense out of it. And if any of you have better ideas, I'd be happy to hear from you. Okay. So these were standard spring dashpot models. Just to set the parameters, we use a scaled spring constant. In this, everything is going to be scaled by particle mass, acceleration due to gravity, and diameter of the particles. This was 10 power 6, which is fairly large. Okay. E was 0.6. We varied this, and it didn't matter very much if we made it softer. Okay. E we set as 0.6, but once again we varied it from 0.8 to 0.4. It didn't make much difference. And the coefficient of friction was 0.4 in all of our simulations. We also did the Hertzian model, similar parameters. You don't have a constant E, but we set the gamma n to some particular value. Okay. So this was a simulation box. Many people have said it's a bad idea to have periodic boundary conditions, but that's what we had in the simulations. So X is the flow direction, Z is the cross stream direction, and Y is the span-wise direction. And the box size was fairly large. We went up to 160/80. Okay. So periodic in the streamwise and the span-wise direction, a bottom rough base and a top free surface. And I'll show results only for 32,000 and 64,000 particles. So this is fairly tall piles, 35 and 70 particle diameters, but we've gone to 2 and 4 times that. And those are fairly intensive computations, but the results don't differ very much. And the important thing here is that we have a random base configuration in which we change the base roughness as follows. Okay. So the initial state in all these simulations is that we take a box that is vertical and then drop particles down at random locations and up to the height that is desired. Okay. The base, we have a vertical box again. We sequentially drop particles into the box, and then we select a layer of particles from within. Okay, this dense packed, it's more dense packed than it looks here, but we select a layer of particles, and we use this as the frozen base. Okay. And the base roughness is varied by varying the ratio of the base particle and the moving particle diameter. So we systematically vary this from 1 to 0. 0 is a flat base. Okay. And we use a random base configuration, as I showed you earlier, and typically we average over 3 such different random base configurations for our results. And as you would expect, when the base particle diameter is 1, you would expect a bag mode profile, okay, with a disordered flow in between, and that is precisely what we get. And as we keep decreasing the base particle diameter, we get a similar profile until we come to some particular value. Okay, so this is the side view and this is the top view, and it shows you that it's a random arrangement of particles in some disordered flow, and you decrease this by a little bit, okay, and you get to a layered state where you have particles in plane arranged in some hexagonal fashion. Okay, and then if you reduce it further, it sort of remains the same. Okay, unfortunately, I don't have time to show a movie, but this is what it looks like. There's only 2 different types of pictures that you see. One looks like that, and the other looks like that. And this happens pretty sharply, as you can see. This number varies by about 1%, depending upon random base configurations that you use.
Where was the top plane? Is that the center?
I'm sorry?
Is that picture through the center?
Yes. So this color is somewhere here. It's cut through the center.
Actually, I meant the other way around.
Yeah, okay. No, this is the angle of inclination. So this is the inclined box, and you cut it through the center somewhere there, and you look from the top and you see this.
Not for the path surface.
In this case, it is, yeah. But not of the hexagonal close back length. Yeah. Okay.
If that last configuration
There's-
you increase a bit or you decrease.
Yeah. So in this, there's always hysteresis, but that is roughly about 1%. So it is not significant. So it's okay. So I mean, we tried that. We tried going up, coming down, and so on. Depending upon configuration, it varies by 1% or so. Okay. So, but that would be just simulation artifacts or not. Okay. So these two states have very different properties, and I'll try to explain all of those. First thing is, the ordered state flows at a much lower angle than the disordered state. I think that was also mentioned here. And you can see I show the velocity profiles as a function of height for the ordered state, and you can see down to angles of about 13 you can get a discernible velocity. Okay. 13 and 14 is actually it's intermittent, but once you come to 15 degrees, you see that there's a fairly smooth velocity profile. In contrast, the disordered state flows at angle greater than 20 degrees. Okay. 21 is when you get a steady flow, but 20 degrees it starts to flow. Okay, you see layering in the ordered state. Okay, so I show here at the bottom ratio of particle base diameter to particle diameter 0.62 and 0.61. 0.62 you see some layering at the bottom, but there's none as you go up, and at 0.61 you see a nice layered structure. Same thing happens for the larger system. Okay. And as you saw in the previous graph, you see in layer order. Okay, Q6 is the hexagonal order parameter. You take any axis, the angle with respect to that. You take e power 6i theta, and if it's hexagonal, this will be 1, and if it's random, it will be 0. Similarly, you can define a 3D icosahedral order parameter for FCC and HCP lattices. And in this case as well, you see a transition. Okay. So concentrate on the blue curves. These are Q6. This is for the ordered state. You see it's close to 1. For the disordered state, it's close to 0. You do a depth average, and you'll see this transition in small Q6 as you go from the disordered to the ordered state. There is also something happening in capital Q6, but that the magnitude is still relatively small compared to the 0.6 that you would expect. This one was counterintuitive to me. The ordered state is actually more dense, and you would have seen it carefully in the picture if you'd noticed that the ordered state actually had a lower height. Okay, yeah, the volume fraction is actually higher, okay, than for the disordered state. The disordered state has a volume fraction of 59% that we're used to. And these variations are actually real variations. Okay, they're not. And this shows you the transition in the volume fraction. In both cases, you find that the Bagnall law applies. So the symbols are the velocity profiles from simulations. The lines are what you'd expect from the Bagnall profile, provided you add in a slip velocity at the base. Okay, the Bagnall law applies in both cases. For the disordered state, it is relatively, the velocity is small. You see a discontinuous jump when you go from 0.61 to 0.62, okay, into the ordered state. And the strain rate is actually independent of base particle diameter. Okay, the difference is only in the slip velocity. If you plot the strain rate, it's roughly the same. And this shows you the Bagnall coefficients. The thing it shows is that the Bagnall coefficient decreases by about 2 orders of magnitude. So this is an ideal system. Okay, so this is another plot of the Bagnall coefficient now versus volume fraction. This is the ordered branch, higher volume fraction, lower Bagnall coefficient. Okay. Disordered branch, lower Bagnall volume fraction and higher Bagnall coefficient. We did some studies on polydispersity. This transition still persists. This shows you the result for 5%. You tried for 10% polydispersity and you still get transition. Though the point at which it undergoes transition differs, you can suppress the transition by choosing particles to be in ratio of 1:1.4 or something. But small amounts of polydispersity don't seem to make that much difference. Okay. So far what I've shown you is that you have two different states. So I started off saying that I wanted to look at how the base affects the flow profile from a shearing layer to a homogeneous flow. So far we have seen that both of them look like Bagnall profiles. So then we went on to look at the developing velocity profile. What happens as the velocity increases from 0? And there you see two very different results. Okay. For the disordered flow, you sort of see homogeneous shearing throughout. Okay. These times are dimensionless times. you will get the time in second by dividing by 100 for particles of 1 millimeter diameter. Okay. So it's shearing throughout, whereas here you can see there's a slip at the bottom and then there's a plug on top for the ordered state as the flow develops. Okay. Now this one, okay, you can actually describe by simple Bagnall equations, except that in my equation I now have an additional term which is the unsteady term. Okay. The stresses are given by the Bagnall profiles. Okay. The way you solve it is that you separate it out into a steady solution plus the transient part. Okay. So the steady solution is known. You have the steady plus the transient part. Similarly, the volume fraction, the steady plus the transient part. And because the Bagnall coefficient depends upon the volume fraction, you have to solve that as well, okay, to a steady and transient part. Put it all in, and you will get a single equation. Okay. We linearize. We neglect terms that are quadratic in the fluctuations, and we will get a single equation for the velocity perturbation for the transient part of the velocity, which contains a time constant, which is related in some way to the Bagnall coefficients. Okay. You can show that this time constant is always positive. That you can show by a theorem that this time constant is always positive, provided the volume fraction decreases as the angle of inclination increases. If the time constant were negative, there's a problem. Okay, you couldn't solve this equation. Okay. So now that the time constant is positive, okay, you can solve the equation using separation of variables. Okay. You get an eigenvalue problem. The solution is actually a Bessel function to the minus 1/3 power. Okay. And you get discrete eigenvalues. Okay. And I show the eigenvalues here. So basically the eigenvalue is the rate at which the transient decays exponentially in time. Okay. So I show the eigenvalues here. The second larger, the second smallest is actually much larger than the smallest one. So that means that if you're at late enough time, you can just include just the smallest eigenvalue alone. So it's called ground state dominance in quantum mechanics. Okay. So if you include just the smallest term and then solve the equation. Okay. So once again, we use the unsteady momentum equation with Bagnall law. We linearized and use separation of variables and retain only the first term in the expansion. The colored lines are the simulation results. The dashed lines are the analytical results. There is difference here. Concavity is wrong at very early times. But once you go to times of greater than about 120, you can see that there is quantitative agreement between the simulations and the analysis. Okay, so the Bagnall law seems to work very well, provided you are at sufficiently late times. In this case, the two earliest times are actually the transient startup times. Okay, so that so just retaining the first term of the expansion gives you quantitatively accurate results. How about the ordered flow? Okay. Here it is very different, the development of the flow. So it's a busy graph. I have shown here the number density profiles in black, the Q6 profiles in red, velocity profiles in blue as a function of height at different times. And what you can see is initially there is no ordering, no layering, little velocity. As time develops, you get an ordered shear layer at the bottom, which is layered and where all the shearing takes place. So you have both hexagonal order as well as layering. And this thing actually progresses. Okay, it goes upwards, it progresses until it hits the top. Okay. But even after it hits the top, the flow still develops, so the velocity still increases, okay, until it reaches steady state. This is like, in real time, it would be about 20 seconds. You can look at the shear layer height versus time, okay, and you see that you can measure it in different ways. Okay, so the point at which there's a transition between a layered and a random structure, that actually increases linearly with time. Okay. This rate of increase of the shear layer thickness is actually independent of the base particle diameter. It's independent of the height. You take 2 times the size, the velocity with which it progresses will be exactly the same. And then it hits the top, and then it stays there, okay, because there's shear throughout the flow. And this shear layer velocity depends only upon the angle of inclination. Okay. Similarly, the maximum velocity, okay, in the flow, as long as the shear layer is moving towards the top, the maximum velocity also increases linearly with time, okay, at a constant acceleration. Okay. This once again is independent of base particle diameter and height. Once it has hit the top, you get back that exponential profile that I talked to you earlier. When I solved the transient problem, you get an exponential profile. You get a similar thing here. Okay. and the velocity evolution with time. Okay, so I show you here the raw data for the velocity evolution with time. There's a shear layer at the bottom and a plug flow above. Okay, and that plug flow, the height of that plug decreases until it hits the top. You can divide the axis by the thickness of the shear layer and the velocity by the maximum velocity, and you can see that there is very good collapse of all of the data. Okay, except at very early times when the shear layer has not really formed. Okay, there is some difference, but after that there is very good data collapse of all of the velocity profiles. And the surprising thing is that I've drawn a line here as well. Okay, and that line is actually the backnode profile. You don't see it because all of it is superposed. So the velocity in the shearing zone is actually very well described by the backnode profile, and that I don't know why. Okay, I've tried various things and I have no idea why that it follows the backnode. Maybe it's not a real backnode profile, but it fits it very well. Okay. So why does it layer? Okay, the layering is actually maintained by the fact that you have particles above and below that are colliding with a layer of particles. Okay, so whenever you have particles above and below which are colliding, I'll just go quickly through this. The force actually decreases as a function of distance, and the reason is because if you have a layer of particles, if you displace a layer of particles a little bit, the temperature doesn't change very much, okay, but the spacing has decreased, so the collision frequency increases. And so there's more collisions from above and less collisions from below, okay, and that tends to bring it back to its original position. And if you go to a continuum approximation where you describe the distance of the layer from its equilibrium position by this parameter u, the restoring force actually goes as a second derivative of u with respect to height. There is also a bending effect due to the lateral pressure. If the system has zero tension, then you'll have no net restoring force which is proportional to u itself, but you will have an additional bending modulus and also a term due to the change in lateral pressure with respect to u. Okay. And if you put all of this together, I don't have the time to go into that, but if you do a linear stability analysis, the system, the layered state is always stable. But because of this destabilizing term, once the amplitude becomes beyond a critical value, the system goes spontaneously unstable. Okay, and that propagates throughout the system. Okay, so yeah, so I'll just put up my conclusions here. The only thing I sort of agree with Renaud that the shearing layer and plug flow for the smooth base seem to be due to flow development, simply because we don't have enough time to watch the flow develop to the full steady state case. At least that is what comes from this analysis. If you wait long enough, the shear layer will ultimately reach the top. Okay, and yeah, and the other important point is that there seem to be distinct flow regimes with universal properties, in the sense that there's no variation of these properties, the shear layer height, the shear layer velocity, the acceleration, and so on. With either layer height or with base roughness, there's only a sharp transition between two different regimes which have very similar properties. Thank you very much.
We have time for one or two quick questions.
Yeah. Right.
What about if there are longer wavelength roughnesses in the bed?
So you do see the transition. We have tried it for waves, and what happens is that the transition height actually first increases with wavelength and then decreases, and that sort of roughly corresponds to what you would expect from a displacement equation of this kind. So we tried it with sinusoidal profiles as well. We are trying it now with step sawtooth profiles.
Yes. Have you tried to plot the pressure divided by the granular temperature as a function of the concentration?
Yes. I mean, there were plots that's basically the Bagnall coefficients that were there. These are the plots. Yeah. These are the Bagnall coefficients for this is the ZZ component.
A new singularity. This is probably
Sorry?
0.74, right?
Sorry.
For the other branch.
Yeah.
The singularity is going to be 0.74. Maybe?
No, it's not 0.74 because it's not hexagonal close packed. It's not FCC. Okay, it's hexagonal close packed in layer, but you have distinct layers. If it were FCC, then it would be constant.
With that, let's thank the speaker.
Thank you.